Okay, so let's have a think about Ksp as it applies to precipitates. In year 11, it was all about, and a little bit of year 12, identifying from solubility rules how a precipitate or when a precipitate forms. So let's just say, for example, we'll take a lead ion. This is from a net ionic equation. And let's put it in the presence of a carbonate ion. That might have been, say, this might have been lead nitrate, and this is, say, sodium carbonate. This is just net because the sodium ions aren't going to react and nitrates never precipitate. So if lead ions are floating around with carbonate ions, you're expected in year 11, I'll just do a one-sided arrow for now, to recognize that you would get a lead carbonate precipitate, and you would write that as a solid. In year 12, you've been introduced to equilibrium and dynamic equilibrium, which tells you that even though that happens in the forward direction and we get a strong white precipitate that you can see settles down on the bottom of the test tube and you say, I got a positive result, carbonates precipitate with lead, even though it sits forward and I get lots of lead carbonate, year 12 has taught you that some of them, a minute concentration, will go in the reverse direction and you will have a small concentration of lead carbonate ions. That's been dynamic equilibrium so far. So what we're actually saying is that once this precipitate has formed as a solid, once I've got that in the test tube, I'm now going to carry on the story. So we pretty much rule off under year 11 and we say, I'm now really interested in what happens with lead carbonate in terms of an equilibrium. So the journey starts with the precipitate. I hope you can see the link there. In year 11, the journey ended with the precipitate. I got one. When it comes to Ksp, the journey starts with that solid in solution. And so we say, well, what would happen now? I'm going to start with my precipitate on the left, and I know that some of it will reionize to its ions. So I'll have a small concentration of lead ions and I'll have a small concentration of carbonate ions. Now, that's an equilibrium and it sits well left. This one is sitting right over here. Now, nothing's changed. If I write it in this direction, of course, it sits well to the product side. Of course, if I'm interested in this one and I sit it here, I say, yeah, okay, well, it's sitting toward lead carbonate. It's favoring lead carbonate. So don't think about this line anymore. I want you to just think about down here. So if I have some lead carbonate as a solid and I was to put it in a test tube with some water, hardly any of it would dissolve because it's an insoluble precipitate. It's going to stay as lead carbonate. It's just not going to dissolve. At that microscopic, minute level, a tiny concentration of lead ions, you could detect it with something like AAS, which comes later in the course, and a tiny concentration of carbonate ions would eventuate. So in other words, we could say the K expression, the Ksp, the solubility product for this highly precipitative and insoluble compound lead carbonate, could be stated as Ksp is equal to the concentration of the product, lead ions, now they're ions so they go in, multiplied by the concentration of the other product, carbonate ions, so they go in. Now you divide that by the reactant if it wasn't a solid. But because it's a solid, you've learnt that you leave solids out. So the Ksp is simply the concentration of the ions of the products multiplied by themselves, and in this one there are no coefficients, so I don't raise it to the power. Now hopefully you can now also see that because we know this equilibrium sits well left, because we know hardly any of the lead carbonate will ionize in this direction, the concentration of lead ions is incredibly low. This number is small. And the concentration of the carbonate ions is equally low. It's in fact going to be the same number because it's 1 to 1. So I've got a very low number multiplied by another low number. And of course, if you multiply two very non-zero low numbers together, you get a really low number. So your Ksp for insoluble compounds will be very, very low, well less than 1, indicating that equilibrium sits well to the left, meaning that this confirms, the Ksp confirms that I have a very insoluble compound. Ksps are very low when you have a precipitate that readily forms. Now the Ksp for lead carbonate is, and I'll confirm it for you, is 7.4 times 10 to the minus 14. See how low that number is? When you multiply the concentration of lead ions by carbonate ions at equilibrium for this system, the Ksp is tiny, meaning the equilibrium sits well to the left, indicating that I get a whole lot of reactant, lead carbonate, and hardly any of the ions will form.